we've looked at triangles and hexagons, let's ask a bigger question. What about any polygon? Is there a formula that always works? Yes, there is. And we're going to discover it using two different methods. Let's start with an irregular hexagon. Place a dot anywhere in the center of the shape. Now we draw a line from the center to each vertex. When we do that, we divide the hexagon into a total of 6 triangles. We also know that each triangle has an angle sum of 180 degrees. So all triangles in this particular picture will be 6 times 180 degrees, or 1080 degrees in all 6 of our triangles. But we do have something interesting happening. At this center point, our triangles form a full circle. Those angles belong to the center point, not to the hexagon's vertices. So we have to subtract them. So I'll subtract out the center. So 1080 degrees minus the full circle, which is 360 degrees, gives us 720 degrees. And that matches exactly what we found in the previous video for a hexagon. Now, let's repeat this process with the pentagon. We draw a center point, and then we draw the edges between the vertices and this point to make our triangles. As we do that, we see we get 5 triangles this time. Each triangle is 180 degrees, so 5 times 180 gives us a total of 900 degrees. But once again, we have this central circle that does not contribute. So we need to remove it, minus 360 degrees. And this gives us that the angles in the pentagon add up to be 540 degrees. If I want to look at this in a general sense, if a polygon has n sides, then it's going to form n triangles. Our pentagon had 5 sides and formed 5 triangles. Our hexagon had 6 sides and formed 6 triangles. Each of those triangles will have 180 degrees, and then we'll need to remove that central circle. So for a general polygon, the total angle sum is 180 degrees times the number of sides minus 360 degrees. Now, let's try a different approach. This time we're going to start with an irregular pentagon. We can choose any vertex of this pentagon, and we're going to draw the diagonals to the other vertices. When we do this, it divides my pentagon into 3 triangles. And each of those 3 triangles has 180 degrees in its angles. 3 times 180 gives 540 degrees. And for this one, each angle of my triangles contributes to the angle sum of the pentagon. There's no central point that I need to remove. So the total interior angle sum is 540 degrees. Let's do this again for a heptagon. We need to pick any vertex, it doesn't matter which, and then we'll draw our diagonals from the vertices to that particular selected vertex. For our heptagon, let's try that one again. We actually end up with a total of 5 triangles. 5 times 180 degrees gives us 900 degrees. So the angle sum of a heptagon is 900 degrees. Let's look at the general form. For a polygon with n sides, the number of triangles is actually n minus 2. For our pentagon, which had 5 sides, we had 3 triangles. For our heptagon, which has 7 sides, we have 5 triangles. So our formula is n minus 2 times 180. This will also give us the angle sum of all of the interior angles of a polygon. I've now found 2 different formulas for the angle sum of a polygon, 180 n minus 360 and n minus 2 times 180. Let's compare these. If I look at this second one and I use my distributive property, I would do n times 180 and then minus 2 times 180. 2 times 180 is 360. They are exactly the same. 2 different ways of thinking, but the same mathematical result. If these formulas feel a little abstract, don't worry. What really matters is understanding where they come from. When you understand the reasoning, the formulas become much easier to remember. And next, we'll look at exterior angles, which lead to another beautiful geometric result.